Hi everyone, I'm RuxinWang from Louisiana State University. Today, I will introduce our work, Preventing Handheld Phone Distraction for Drivers by Sensing the Gripping Hand. It is a collaborative work with my teammate Long Huang and my advisor Dr. Chen Wang. Using a handheld device while driving is a dangerous behavior. The driver can be impacted by all three types of distractions from the phone: visual, cognitive, and manual, which increases the risk of crashing by up to 23 times. Since the COVID-19 pandemic, a 17% increase in driver phone use has been found because more people attempt to take Zoom calls, read Instagram messages, or text while driving. So law enforcement and insurance penalty policies help raise public awareness and lower car accidents. They achieve limited effects. More efforts are still in urgent need to reduce the driver's handheld phone use and further improve traffic safety. This work proposes a continuously phone use monitoring system to eliminate the driver's handheld device distraction. The proposed system leverages active acoustic sensing to detect when the phone is held by the driver's hand and take safety enhancement measures immediately. There has been a rising interest in monitoring unsafe driving behaviors, leveraging the smartphone sensor data to recognize inattentive driving events, such as eating, drinking, and turning back. But none of these works could effectively address handheld device distraction. In addition, some researchers intend to prevent handheld phone distractions by discriminating the phone user to be the driver or the passenger based on its in-vehicle location. However, these methods cannot detect when the distracted driving happens to take safety measures right away. Moreover, there are several solutions to capture phone-driver interactions based on cameras, but these vision-based methods are limited by light conditions, camera view angles, or high isolation overhead. Different from the previous works, we propose to monitor the driver's phone use between the handheld and the hands-free status by directly sensing the gripping hand, which enables eliminating the direction or reducing the impact at once without additional devices. The basic idea of our system is to exploit acoustic sensing with smartphones to discriminate the phone use between the handheld and the hands-free status. Next, determine distracted driving activities and capturing the phone grip, start, end, and duration. As illustrated in the left figure, the sound recorded by the microphone includes the damped direct path signals, the refracted signals, and the airborne refracted signals. These signal components are mainly determined by the material, area, and pressure of the contact surface. Because the hand skin, geometry, and gripping strength are distinct from that of any support surface in the car, the gripping hand can be discriminated by acoustic sensing. As illustrated in the right figure, microphone recorded sound is distinguishable in the waveform among all the 6 phone placement scenarios, which shows the potential of differentiating the gripping hand from the other phone placement scenarios. We also face some challenges when using acoustic signals to sense the gripping hand. First, discriminating the phone's diverse contacting surface. Moreover, robust system under noisy in-vehicle environment. Our acoustic system must be able to work under the noisy in-vehicle environment. Additionally, to accurately estimate the start and end of a distracted driving activity, our system needs to handle the classification errors and the noisy transient states when the phone is being grabbed or dropped off. The architecture of our system is shown in the slide, which takes the smartphone microphone's recording as the input. The data preprocessing is performed first to prepare the data for analysis. It applies a bandpass filter to remove the noises outside of the sensing signal the frequency range, and synchronizes the data by referring to the original audio. Based on that, we can find the start and end of the path signal to obtain the path segment, which contains the information about the phone use status. The core of our system consists of two components. The CNN-based phone use status recognition processes the path sound and recognizes the phone use status at the current sampling point. Based on a series of the most recent phone use data samples, the handheld phone distraction detection further captures the distracted driving instance and determines its timing. The sensing signal is used to interact with the object which in contact with the phone and capture its characteristics in the acoustic domain to discriminate hands-free or handheld status. Each path signal is designed to swipe from 18 kHz to 22 kHz to leverage the rich frequency information. Besides, the high frequency range is not impacted much by the in-vehicle noises. Each path signal lasts for a short period, 25 milliseconds, and every two paths are separated by a stop period, 75 milliseconds. After obtaining the data from the microphone buffer, we first pre-process it for denoising, synchronization, and segmentation. For denoising, we design a bandpass filter with a 18 kHz to 22 kHz passband to reduce the noises outside of the sensing signal's frequency range. The engine, road, and wind noise can be removed, which are mainly on the frequencies below 6 kHz. Next, we run a synchronization schema to precisely locate the path signal in the microphone data. After synchronization, we can find the start and end of the sensing sound by referring to the original path signal. The resulted 25 millisecond path segment is used for further analysis. We derive the short-time Fourier transform, short as STFT, from the path signal to describe the characteristics of the contact object in the acoustic domain. Next, we use the sliding window to compute the discrete time STFT, short as DT-STFT, of the path signal, which results in a 2D image. The bottom figure in the slides shows the feasibility of using the DT-STFT image of the path signal to differentiate 6 different scenarios. We can observe that the DT-STFT images show distinct pixel patterns among all the contact objects. To recognize the gripping hand based on DT-ST images, we develop a CNN-based binary classifier with 3 convolutional layers and 1 fully connected layers, which is a CNN structure widely used on mobile devices. We resize all the DT-ST FD images into a fixed size and input them to the 2 CNN models. The CNN scores of the 2 models are integrated to make the classification decision. This result is the phone use status sampled by one sensing path. That process could be reduce the errors of each single mic and improve system's robustness. Most smartphones are embedded with 2 microphones for noise cancellation. By using the 2 acoustic channels, we can leverage the spatial diversity to capture more characteristics of the contact object. Therefore, we separately train 2 CNN models for the phones Mic 1 and Mic 2. We continue to investigate the practical phone use monitoring and correct the sample errors to couple with the false positives and false negatives in the classification results. The phone status monitoring results is a sequence of labels between handheld and hands-free, based on which the system decides when the user grabs or drops off the phone. We design an adaptive window-based error correction filter, which consists of 2 steps. First, we detect the status changes and find adaptive windows. Then, we correct the status classification errors with the flip and merge rule. For example, after getting the predict label sequence, we found that There are classification errors due to the transient states when the user grabs and drops the phone. To correct these errors, we first find for adaptive windows. Next, we use toThreshold to select the small windows and flip the labels in that windows and merge to the adjacent big windows. Here is the corrected result. Finally, the comparison between corrected result and ground truth shows that our filter is very efficient. Next, I will introduce the experiment setup of our work. We use 3 smartphone models and 2 car models. We develop an experimental platform based on Android 9, which periodically sends ultrasonic fast signals and records the stereo sound simultaneously, and the microphone sampling rate is set to 48 kHz. The overall performance is evaluated based on 14 participants, 11 scenarios. Moreover, 4 typical vehicle environments, city driving, highway driving, engine off and engine on, are tested and compared. We also investigate the various impact factors from the device model and the car model. Additionally, the impact of the car audio is studied. Furthermore, we monitored 4 participants' phone use while driving on the highway. The RC curve of our system to recognize the phone use status are presented in the slide. We found the system achieve a high true positive rate and a low false positive rate to discriminate handheld from hands-free. When integrating the 2 microphones, our system achieves 98.4% TPR and 0.5% FPR, and the equal error rate is 1.1%. The result is very promising, as the system correctly recognizes the handheld and the hands-free scenarios, regardless of how the driver uses the phone and who holds the phone. Next, we investigate how the system discriminates each of the 11 phone scenarios between handheld and hands-free. Red figure presents gripping hand detection rate in 4 handheld scenarios and 7 hands-free scenarios. We observe that our system performs well for all 11 scenarios, obtain a mean 99.8% detection rate. The result indicates that our system successfully classifies the phone use scenarios based on their contact with the phone. We investigated the impact of the device models. Left figure shows the classification accuracy for each device. Google Pixel 2 performed the best with 99.6% accuracy. The performance of Samsung Galaxy S8 and Motorola J8 are slightly lower, which are 98.9% and 99% respectively. The results indicate that our system can be broadly deployed on different devices. Similarly, the shells and interiors of different car models may affect the performance of our system. Red figure shows the performance of each car model. Car B achieves an accuracy of 99.6%, which is slightly higher than Car A. The reason may be that Car B has a thick shell, which suffers less from the wind, road, and engine noises. The result shows our system can detect distracted driving with different car model. We evaluate our system under different engine status, including city driving, highway driving, engine on, and engine off. As the left figure illustrated, engine off performs the best with 100% accuracy, as this is a quiet in-vehicle environment. Engine on also performs well with 99.8% accuracy. City driving and highway driving achieves a slightly lower accuracy, which are 98.9% and 98.8% respectively, though they suffer from different types of noises. The results indicate that our system is robust enough to detect the phone use distraction in both driving environments. When driving, the drivers may turn the radio or music on. The car audio sounds may interface our sensing signal and affect the system performance. As the right figure illustrated, the classification accuracy decreases to 97% when the music is on, which is still high. The result confirms the robustness of our system to work under car audios. Lastly, we conduct a case study to monitor 4 participants' phone use during highway driving and detect their distracted driving activities. Our system achieves 99.5% detection rate to capture all the distracted driving activities of these participants, and the false positive rate is 0.4%. Our system achieves a median error of 0.76 seconds to determine the start of a distracted driving activity. The median error to determine the end time is 0.55 seconds. These errors are mainly resulting from the transient states when the user grabs and drops the phone. The result confirms that our system is effective to monitor the driver's phone use. Here is our conclusion. We present a phone use monitoring system to address handheld phone distractions by sensing the use of the gripping hand. We derive the short-term Fourier transform of each pass and develop a CNN-based binary classifier to discriminate handheld and hands-free. We design an adaptive window-based filter to capture distraction activity and determine its start, end, and duration. Extensive experiments show that our system can achieve high accuracy in detecting the smartphone handheld status and accurately capture the start of the distraction period. That's all for today's presentation. Thanks for your time.